Hi, this is Ms. Fitzmaurice, and this video is an introduction to circuits. So by the end of this video, you should be able to define voltage, current, resistance, and power, and explain how they're related in an electrical circuit. You should be able to solve basic circuit problems using Ohm's law and the power law, and you should be able to recognize the symbols for basic circuit elements and use them to make circuit diagrams. Alright, so before we start getting into complicated circuits and the math of circuits, let's just take a minute to talk about why a light bulb lights up in the first place. Okay, so you also saw in class on Friday that you needed to connect the light bulb to both ends of the battery, and you saw that you needed to connect the light bulb on the side and also on the bottom of the battery. In order to answer this question, we have to think back to chemistry. So we know that every single atom is made up of protons and electrons, and that protons are positive and that electrons are negative. And in chemistry, your chemistry teacher probably told you that like charges repel and that opposite charges attract. Now, thinking about this in terms of physics, imagine you have two positive charges, so two protons, for example. What they're really doing when your chemistry teacher said that like charges repel, they're each exerting a force on each other in the opposite direction. And when your chemistry teacher told you that opposite charges attract, so say you had an electron and a proton, they're pulling each other towards each other with some kind of electric force. And this force that they pull each other towards or use to repel each other away, if you think about it, it's a lot like gravity, because in order for the Earth to pull you down with gravity, you don't have to be touching the Earth. Okay? In order for the sun to be pulling the Earth towards it, the sun is not touching the Earth. It is a force that happens at a distance. Okay, so in a lot of ways, what we're going to call Fe, the electric force, is a lot like the gravitational force, or the force of universal gravitation. And even if we compare the two equations, so we know the equation for universal gravitational force is equal to Fg equals capital G mm over r squared, okay, and these are the masses of the two different objects, so you need two objects, and in gravity they're always attracting each other, and it also depends on the distance squared. Okay, so the bigger the masses, the bigger the forces. With the electric force, it's almost the same format. So you have Fe equals, and instead of being dependent on masses, it's going to be dependent on charge. Okay, so Q1 and Q2 here are the charges of your particles. So if you have a bigger charge on your particle, then you will have a bigger electric force. And just like in gravity, it depends on distance squared. And then both of them have these kind of universal constants, and they are always a certain number. So don't worry too much right now about what those numbers are, but it's basically just a number that always goes out front. Okay, so you can see they're both forces at a distance, and they kind of have the same structure. It's something, some character of object 1 times some character of object 2, whether that character is the charge or the mass, and then divided by the distance between them squared. Now, much like the fact that gravitational force leads to gravitational, I'm just going to abbreviate it, gravitational potential energy, the electric force is going to lead to electric. And again, I'm just going to abbreviate potential energy. And remember that gravitational potential energy, UG, is equal to minus G mm over r. Okay, so we're dividing by the distance instead of the distance squared. Electric potential energy works pretty much the same way. It's kind of off by a minus sign, but it's going to be Q1 times Q2 over, again, these constants, 4 pi epsilon naught times r. Okay, so now the question is, how does this relate to a light bulb? And particularly, how do these forces and these potential energies relate to the voltage that you see on the side of your battery? Okay, so let's think about forces. We know that all atoms are made out of protons and electrons. And in general, if you have a bunch of electrons together, and there are some parts of the battery in which you have too many electrons together, and they're going to repel each other. They don't really like each other, and they want to move along the battery, or away from each other. And if you connect them with a wire, if you remember from chemistry, electrons in a metal are free to move around. So if you connect them by a metal wire, the electrons will be able to move around away from each other and towards the end of the battery where there are fewer electrons. Okay, so protons are big and heavy, they don't move. Electrons move around, and inside your battery you have basically a collection where there's too many electrons, they don't like each other, and they move. If you allow them to move through a metal wire, they will move to get away from each other and towards the positive end of the battery. And this movement is, of course, because of the electric force. Okay, so now the question is, what about voltage? We don't usually think about a battery in terms of the force each electron feels, but we know that in general, force means that there's probably, as long as it's some kind of sustained force, means there's some kind of potential energy. And what voltage is potential energy per charge. Okay, so you can think of it kind of as like a potential energy density, but it's just potential energy per charge is what voltage is defined as. And in particular, it's electric potential energy per unit charge. Alright, in terms of units, hopefully at some point in your life you have seen voltage, and the units for voltage is volts. Okay, the unit, of course, for our potential energy just like all potential energy, is J, joules, and charge, and the symbol for charge is usually Q, is coulombs, Coulombs. Okay, and the abbreviation is just C. Okay, so when you see voltage on the side of the battery, all it means is electric potential energy per coulomb. Now, one thing that can be a little bit confusing is that one electron does not have 1 coulomb of charge. Okay, one electron has, in fact, 1.6 times 10 to the minus 19 coulombs of charge in it. Okay, so as long as we're dealing with atoms, this is the smallest unit of charge that we could talk about. And one proton would have exactly the same amount of charge, 1.6 times 10 to the minus 19 coulombs. Just when we're talking about an electron, we have to put a negative sign in front of that charge. If we're talking about a proton, we put a positive sign in front of that charge. Alright, so the other things that I said I was going to talk about are current, resistance, and power. Current, if you think about current in terms of like the current of a river, you think about how fast is water flowing through the river. Current in terms of a circuit is basically the same idea. It's how quickly charge flows through a circuit the symbol for current is I, and the unit is amperes, or sometimes just amps, or A. So amperes, sometimes you'll see them as amps, and sometimes it's just abbreviated as A. And that's the number of coulombs per second that flow through your wire. Alright, resistance in a circuit is basically as your electrons are flowing through the wire, they come across atoms that have their own electrons, and sometimes they get sent back. And so this, you can kind of think of it as like friction or resistance on a microscopic scale, as electrons are trying to make their way through a metal wire, or actually any other kind of material. So if this is our wire, our electrons are sometimes going forwards, most of all going forwards, but sometimes they get sent backwards. And this idea is called resistance, and it's basically a property of the material or the object electrons are trying to flow through. That tells you how difficult it is for them to flow. Okay, and so this is my picture of electrons kind of coming through a wire. The big circles represent atoms that are maybe sometimes deflecting our electrons. My little circles are atoms. And we have to think about resistance in terms of energy. Okay, so if you are an electron, you start out, you're on the negative side of the battery. You start out with a lot of potential energy. Okay, you have this force from your repulsion to your other negative charges that pulls you through the wire to the other side of the battery. Okay, so you have a lot of potential energy over here. Then you get kinetic energy because you're pulled by the positive charges, repelled by your negative charges, but kind of like friction, you lose energy to heat because of resistance. Okay, so our symbol for resistance is R, and the unit for resistance is actually called ohms. And instead of writing the word out, people often use this kind of like upside down horseshoe, which is the Greek letter omega. And that tells you the resistance of the thing your electrons are trying to go through, whether it be the wire or your light bulb or a toaster oven. And that takes energy from the electrons. They lose energy due to heat as they're slowed down by the atoms in the object. Okay, and then the last thing we're going to talk about is power. And just like in, normal energy that we've done before, power is going to be energy used per time. So it's energy used up by a circuit per unit time. And just like before, the symbol for power is a capital P, and the unit is watts, or just W. Alright, so our next equation is how these all fit together in an equation. Okay, and if you think about it, let's think about what would make the current, so I remember is the current, go up or down. Okay, so remember this is how fast charge flows through our circuit. And you would expect that if you had a big potential energy or a lot of voltage, a big potential energy per charge, that you would have a lot of current. So that's going to be directly proportional to current. And then you would also think that the bigger the resistance is, the more your material stops the current, the smaller it's going to get. So our equation that relates these guys is actually going to be this way. Okay, so we will have a big current if we have a large voltage. And remember that's charge, or that's potential energy per charge. And if we have a small resistance, okay, and so we have voltage V, resistance in ohms, and current in amps. And this is one arrangement of what is called Ohm's law. okay? But actually, sometimes, depending on their temperature or what other things they're interacting with, the resistance of objects can change. And so the more proper way to define Ohm's law is R, the resistance, is equal to the voltage divided by the current. And you notice that these two equations are equivalent to each other. All I've done is I've cross-multiplied the I and the R in order to switch their places, but they're algebraically equivalent. Now, in terms of power, we know that in general, power is equal to the energy used, or work, divided by time. So let's say energy over time, and we want to somehow relate that to current, voltage, and resistance. So we know that in general, our voltage is really energy per charge. Okay, so we would like to be able to have energy divided by time and somehow get rid of the charge. Notice that if we multiply by I, which is charge divided by time, so that's our current, that our charges will go away and we're just left with energy divided by time. So in general, the power law is P equals IV. Power is equal to current times voltage. Alright, the final topic in this video is drawing circuits. Okay, so the first thing is we need to draw different circuit elements. And so we'll start with a wire. We represent a wire with just a... to represent a battery, you'll see a couple of different symbols. They all have the same basic structure. Okay, and so you have a wire leading into a large line followed by a small line. In general, the side with the bigger line represents the positive end, and the smaller line represents the negative end of the battery. You will sometimes see a series of large and small lines. And so again, the side with the biggest line, vertical line, represents the positive end, and the smallest line represents the negative end. So this is a battery, and I'm going to circle in green. This is the battery part with wires coming out, and this is the battery part with wires coming out. So this is how you represent a battery. To represent any kind of object inside of your circuit that is a resistor. So a light bulb, or a toaster oven, or a hairdryer, or anything like that, we represent it like this. And again, the green part I'm circling right now is the resistor, and then the two horizontal lines coming out are just wires. And the last circuit element that we're going to talk about later, and just briefly, is called a capacitor. And for now, I'm going to say it kind of acts like a timer in your circuit. So if you wanted to draw the circuits that you created on Friday, the very simple one where you just had one light bulb connected to the battery, so most of you drew it kind of like this. You had a light bulb and then a wire connected to the battery. This is how you would draw the circuit. You would have your battery. I'm just going to draw the two-line battery. Okay, and you are connecting it to a wire, and our light bulb is a type of resistor, so this is the circuit that we would draw. Okay, for two bright bulbs, you would have a battery connected to one bulb, and then also connected to a second bulb. And even though both bulbs are directly connected to the battery, we can draw it like this because wires are direct electrical connections. Okay, and then two dim bulbs, so this was too bright. Two dim bulbs you would draw like this. You had one connected one after another to the same battery, and electrons had to flow through each bulb to get back to the other side of the battery. The very last circuit symbol I'm going to draw in, and we didn't really have this in our circuits that we had on Friday, is ground. And we will talk more about what that means a little bit later. But for right now, I'll just say that's like our 0 volts or our reference point.